Hi, welcome to Talks at Google in Cambridge, Massachusetts. And today I'm delighted to introduce a two-for-one topic. First is Abraham Flexner, who's a person that I think we should all know better, the first director of the Institute at Princeton and one of the people responsible for bringing Albert Einstein to this country, among many other things. Very famous in his time, front page obituary in the New York Times. And we seem to have forgotten about him, a fascinating person, and then the author of the original classic essay. And here to comment and expand on that, Robert de Graaf, the current director, Institute of Advanced Studies at Princeton, certainly an accomplished scientist in his own right, director and Leon Prevey professor at the Institute since 2012, a mathematical physicist, well known for string theory, and also the advancement of scientific education. And so he's past president of the Royal Netherlands Academy of Arts and Sciences, in that capacity an advisor to the Dutch government, advocate for the science and the arts. He has received the Spinoza Prize, the highest scientific award in the Netherlands, and has been named a Knight of the Order of the Netherlands Lion, member of the American Academy of Arts and Sciences and the American Philosophical Society. So heartfelt welcome, Robert.
Thank you so much. Thank you, Richard, and a great pleasure to talk here about a very small book. So it'll take you, I think, only an hour to read. But I think it's a small book on a very large topic, namely the role that basic research plays in our lives, and in some sense on deeper themes like curiosity and imagination. It's great to be a co-author with Abraham Flexner, who indeed needs, I think, in some sense, we have to resurrect his legacy, and indeed he was famous for bringing Albert Einstein to the Institute. So when this book came out, I thought it would be a good idea to see whether we can have a blurb from Einstein about the book, because they must have known Flexner well. So I was envisioning Einstein. I really recommend that book. I think it was a perfect occasion to do so. So then I looked in the Ultimate Quotable Einstein, which has almost 600 pages of Einstein quotations on everything. Whether there was anything about Flexner, there was one quotation, and it said, one of my few enemies. So that was my proposal to have on the book, I think, but we didn't go there. Flexner wrote this essay, The Usefulness of Useless Knowledge, which really has a catching title. He worked on it for many years, in fact almost 2 decades. It was finally published in October 1939 in Harper's Magazine. And it's interesting just to see what was relevant in October 39. You see one of the issues here, well, there was an article about conscience in wartime, but it was also an equally important article on why can't we have perfect teeth, or old people arising natural problems. So the world was in crisis, but in some sense it's still remarkable that he was writing about the use of basic research, the usefulness of basic research in that time. And in this book, I started the book by explaining that 39 was special too, because it was actually the year when the World Fair came to New York, and the theme was the world of tomorrow. In fact, it returned in 1964, but it was in Queens, and it really was a way where many people could meet new technology. For instance, the first television broadcast was there. At that point, there were 200 television sets, and the first live broadcast was the opening speech of President Roosevelt. The dishwasher, the fax machine, they were all introduced to the American audience for the first time. On the other hand, there was things of days long past. For instance, kind of a beauty pageant of steam engines. And another thing, the first robot was introduced. His name was Electro. He could smoke a cigarette, and he had a little robot dog, Sparky, that you could play with. And here you see him performing a...
Electro, come here. And here he comes, ladies and gentlemen, walking up to greet you under his own power.
Not that impressive, but I think it was actually his, the voice was by playing gramophone records. So this was 1939 technology. But actually, there was a second opening speech, and that was by Albert Einstein. Albert Einstein decided to talk about cosmic rays, and it has been described as a comedy of error, because the trick was that cosmic rays, particles coming from the universe, were captured in the Hayden Planetarium in Manhattan, then sent by telephone, whatever that means, to the fairground. And when the 10th cosmic ray was captured, a big switch was thrown, and then the fuse blew, and the whole room turned pitch dark. And the New York Times then reported the next day that the audience left this kind of exposition about science to go to something they could applaud. So it was kind of not a great success, but I think it's amazing because Einstein was talking about the world of tomorrow, but he didn't mention two topics. He didn't mention nuclear power, nuclear energy, and he didn't mention computers. And both of them actually were at that point really developed under his own eyes in the Institute for Advanced Study that was set up by Abraham Flexner. So the institute was set up, founded in 1930. The first professors came in 1933 as a kind of an island, a paradise for scholars. As this New York Times magazine article describes, seeking eternal truth in a world of chaos. But little did Einstein or Flexner, who was the first director, realize that he was actually creating these kind of terrific developments that would totally change the world. So only a few months later, the opening of the World Fair was, I think, in April. In August 1939, Einstein would write his famous letter together with Leo Szilard, asking President Roosevelt to develop the atomic bomb. And the Manhattan Project basically got underway in October 1939. Flexner does refer obliquely to atomic power, but he wasn't aware, I think, that this was kind of happening. Another development in the 1930s was that Princeton became a center for mathematical logic. Church, von Neumann, Gödel, Turing, of course, was a graduate student there. And von Neumann actually, working on the abstract computing machine, proving mathematical theorems, realized a few years later that building an electronic computer, as you know very well, is much more efficient using the von Neumann architecture, that is to say, allow the computer to be programmable. And he built actually the first prototype of that at the Institute. Here you see him with Oppenheimer in the inauguration of the IES machine. It's quite a remarkable thing. It had a 30 by 32 memory. It was built from war surplus material, because of course you are not going to spend this real money on building this computer. And in fact it was a triple helix effort, because it was supported both by philanthropy, by the war effort, and by companies, RCA and later IBM. In fact, von Neumann not only did huge simulations of the hydrogen bomb, he also used that computer to do the first electronic weather forecast, this and the machine in pen. So this is the first computerized weather prediction from January 1949. I like to indicate it took these days 48 hours to predict tomorrow's weather. So it was yesterday's weather actually, which was pretty good on the 30 by 32-bit machine. And this institute, which was supposed to be as far removed from reality as possible, had, here's the floor plan in 1948, that Einstein, being the father of the peace movement, it had von Neumann being partly a role model for Dr. Strangelove, and building the coldest of cold warriors, and Oppenheimer, who was kind of caught in between. So it's the perfect case to demonstrate the title of Flexner, that this kind of useless knowledge, whether it's abstract mathematical logic or understanding the quantum mechanics of atomic nuclei, could have incredible, useful, and also dangerous consequences. So who was Abraham Flexner, this man that we basically forgot about? So he was born in a poor Jewish family, immigrant family, in 1866 in St. Louis. He had 9 siblings. 3 brothers became pretty famous. Simon Flexner was the first director of the Rockefeller Institute, now Rockefeller University. He was a medical doctor. Bernard Flexner was very seriously involved in politics. And Abraham Flexner, he was the one who was able to go to Johns Hopkins University at a very young age, at age 17, graduated in classics in 2 years, went to start back to St. Louis, created what became a high school teacher, became notorious because he was failing at 1 year his full class, which actually made the headlines in the local newspaper, started when he was age 23, his own high school, and then became famous by the so-called Flexner report, a report he issued in 1910 that looked at all 155 medical schools in the US and effectively led to the closure of 120 of them. Medical education at that time was a disaster. It was for profit. It was an undergraduate course. Students would not see any patients. It was just basically a scam. And he minces no words. I think Chicago is described as the plague spot of the country. But even very established medical schools, like here at Harvard, they essentially closed down and started again. Johns Hopkins, which was the first modern research university, was the only one of the few, I think, that was a lightning example. And then Flexner started to think about universities too. And he became a very influential thinker about modern American universities, criticizing the kind of shallowness, the lack of research culture in universities in the 1920s and 30s. He's, for instance, describing Columbia and telling that, we can see that Columbia at that point offered courses in practical poultry raising. So this was the early 30s. This was a time that, people were really looking for jobs. And then came the moment which really made him move from an abstract theoretical critique to actually do something. He was able to start the Institute for Advanced Study thanks to a wonderful grant by the Bamberger family, who sold the department store they had in Newark department store in 1929, a few weeks before the Wall Street crash. So they were one of the few philanthropies that actually had cash. And then actually the Institute became quite influential because geopolitics intervened. Of course, 1933, certainly there's this wonderful group of German scholars, Jewish German scholars, political refugees, who were in search of a home. And the Institute became kind of an Ellis Island, attracting scholars from across the world. Here you see some of the, it's difficult to read, very small grants were given to these great names. So you could kind of buy, so to say, a Kurt Gödel, I think, for $1,200, or the greatest logicians from the last 2,000 years, or Stan Ulam, the Polish mathematician that would design the hydrogen bomb. I think he has an 800. And the joke is that there was something, there were again, the Bamberger family that had this department store was again dealing in distressed merchandise, but now scholars. And Flexner here writes in 1939, I think very perceptively, that 50 years from now, historians looking backward will, if we act with courage and imagination, report that during our time, the center of gravity in scholarship moved across the Atlantic to the United States. And it's good to remind ourselves that the centers of scholarship have moved across the globe through the centuries. He makes a perfect argument, and as I said, as I said in the introduction, when he dies in 1959, the New York Times writes actually that no other American of his time has contributed more to the welfare of this country and humanity in general. So quite remarkable to see that somebody with such a large reputation is in some sense forgotten. And I think he should not be, because the argument he makes is timeless. It's the argument about the usefulness of useless knowledge. He spends a lot of time arguing, for instance, about electromagnetism, Faraday and Maxwell. There's this famous quote, not sure but it's true, that when the British Chancellor of the Exchequer visited Faraday's lab and asked, what's this good, Professor Faraday, all this electricity? He said, I've no idea, but one day, sir, you will tax it. And he was right. You could say that these days, electricity, everything is governed by electricity. Another example, quantum mechanics. So if you think of the birth of quantum mechanics, so Max Planck famously said that it was an act of desperation. He really wanted to save the laws of physics, and he had to do this crazy thing. He was willing to make any offer to the principles in physics that I then held. It was an esoteric subject for just a handful of people. And of course, these days, it's estimated that 30% of GDP, but it could be higher, is in some sense directly connected to the results of quantum mechanics, whether it's integrated circuits, nanomaterials, lasers, and of course, with the advent of quantum computing, this only will increase this percentage. The life sciences. Now, I think any breakthrough we have seen in life sciences, whether it's the discovery of the structure of DNA, of genetic code, gene editing, it all was curiosity-driven research. And perhaps the biggest story in the last few hundred years has been the tremendous progress in health. So the fact that lifespan, life expectancy in the West basically tripled in 250 years. It's an amazing fact of history. It's not sure where it's taught in history courses because it's something that takes place over centuries. But because of hygiene and medical research, that actually made a tremendous impact on the lives of everyone. And in fact, there is another thing which that would be the next book, would be about the uselessness of the usefulness of useless knowledge, because it's like a third order effect, and that this very practical thing give rise again to basic research. And my favorite example is superconductivity. Superconductivity was discovered in 1911. If you cool materials very cold, electric current starts to go basically at no cost, which means that you can build very strong magnets. Well, these strong magnets, of course, are used in transportation, but they're also used in fMRI scanners. And you could think of the whole field of neuroscience only could develop because of these incredible progress in magnets. And these days, many quantum computer elements also, of course, really use these magnets and these very kind of low temperatures. But the best example, the place we think in the universe that is the coldest place in the universe and has the largest magnet is actually the Large Hadron Collider in CERN Geneva. And it's because of the magnet technology and the superconductivity being used there that actually it led to the discovery of the Higgs boson. And remarkable, the theory behind the Higgs boson is a very close relative to the theory of the superconductivity. So in some sense, we went through a full cycle from an abstract physical discovery through applications back to fundamental physics. And it's good to remind that Peter Higgs, even in physics itself, there are long timelines. Now, it took 50 years from the original idea to the Nobel Prize. So the first decade he was totally ignored. Then there was a decade where people really read the paper, became interested. Then another decade designing the machine, a decade building the machine, and a decade running the machine. And when Peter Higgs, at the announcement said, with tears in his eye, that he was happy to see the discovery in his lifetime, I think it was 84 at that time, he was very serious. Now, it could easily have took another decade or two. Another good example is the discovery of gravitational waves that we all have witnessed. Roughly was announced a year ago, but the discovery was in September 2015. That was a 100-year prediction by Albert Einstein. So he didn't live to actually see this. But of course, we, as a human society, we did. I always like to think, in some sense, cosmologists are a good framework because they know exactly what they don't know. As you know, in cosmology, we know that roughly 5% of the content of the universe is known. It exists of known material. There's 95% still to be discovered. And I think this is exactly what cosmologists want to do. So I feel, in basic science, we are a little bit like the old explorers. It has these kind of wonderful maps. Part of it was covered, but then there was a large part which was unknown, and these cartographers would draw these kind of sea monsters in it, right? Because that's, our imagination fills that empty space. But the role of basic science is to explore this. And I want to argue, and I think you are probably preaching to the choir here, but it's that we are in some sense in a more exciting moment in a time of basic research, because often you can frame it like this: what is the most important thing ever discovered in science? And one way to phrase this, suppose the world would kind of disappear, and you're still able to communicate one line, say one Twitter message, to the next generation. What would the hint you would give to the next generation of budding scientists? And my line would actually be this: that all matter on the Earth and in the cosmos consists of particles 1 billion times smaller than everyday objects. The fact that we have discovered the building blocks of matter, of life, is incredibly important. I always think, suppose you give a child a toy, you can give it a metal car of one made of Lego blocks. And if you go back to that child, the two children, a few weeks later, the one who was getting the Lego actually would build something else. So I think actually we are now in a phase where it's really a matter about what are we going to build now that we discovered the building blocks of nature. And we see this, in the material sciences, where now we can basically build materials atom by atom. We see this in the life sciences, where we have synthetic biology can produce things that only imagination can think of. So I would like to say, in the old model, where the sciences are exploring nature, and we kind of know what we don't know, so we want to cover the whole map. We are now in a stage of development where we are not looking at nature, but we're building nature ourselves. So it's basically the space of everything we can make and how we find our ways in this kind of vast space. And I think that is the exciting moment where basic research is. So why would you have basic research? And I think we can revisit Flexner's argument. Well, I think the first and foremost thing to say is that clearly we want to argue that knowledge, in and of itself, is incredibly important. And that's true for the sciences, it's true for the humanities, it's true for the arts. But there are some extra layers, and that's exactly where Flexner, and I'm trying to add to it, is we know that basic science develops new tools and techniques. As a particle physicist, I'm obliged then to say that the World Wide Web was developed in terms of facilitate the communications through thousands and thousands of particle physicists who, in the original model, were not able to read each other's web pages, but also write on the web pages. Then, of course, it's attracting the best minds who then can go out. Again, here I have to say that theoretical physicists went into the financial markets and basically destroyed the world, I think. So I should give them credit to that. Also important to realize is, certainly here, I think, as you know, it's very difficult to capture the full profits of basic research, because they will flow across disciplines, they flow across regions, across countries, across generations. And so in many ways, it's a true public good. Economists have not done a good job in putting the right numbers there. So if you ask the economists, what is the investment, the return on investment of $1 spent on basic research, you get all kind of numbers, between 4 and 15. But it's a big multiplier. And I would wish, in some sense, we could argue more, particularly, I think, because it's, without a doubt, as I said, it's a public good, and it's something that, in the end, I think, needs to be publicly supported. And of course, it leads to plenty of innovation startups, and here in MIT, close to MIT, we are, in some sense, at kind of the very epicenter of this tremendous effort, and you are, in some sense, the embodiment. This Google is, of course, an embodiment of this. But if we see, how federal and, for instance, support for research has developed, and I can imagine Flexner coming back and tell us, okay, tell us what happened in the intervening years. The first part of my story would be very positive. Of course, he has seen that after World War II, there was this terrific current of support. There was the famous report by Vannevar Bush, Science, the Endless Frontier, that led to the creation of the National Science Foundation, not only in this country, but across the world. Incredibly increase in basic research with not that many strings attached. And that kind of peaked, as you see on this graph, as a percentage of GDP around 64, which was the height both of the Cold War and the space race. And then it went down, and it has been basically a steady decline. It's some sense even only vaguely correlated with the political color of the administration. And we see this, and we see that in some sense the defense and non-defense components have been roughly in balance. So roughly 50% of what this country spends on research and development will be defense-oriented, the other one is not. If you look, for instance, at the National Institute of Health in real dollars, apart from the stimulus money in 2009, it had basically declined by roughly 20-25% over the last 15 years. And of course, at this point, as you know very well, it's threatened by even more severe cuts with the present so-called skinny budget of the current administration. But this has been a worrying trend. If you look at the share of R&D expenditure by the various resources, you see also that the corporate world, in some sense, has never been very, very strongly supportive. It roughly now spends, I think, 6% of all R&D money on basic research. So it's typically something that where public funding and philanthropy and universities play an incredible role. And if you talk to the next generation, young scientists, there's a lot of complaint. I mean, they are worrying about about grants, about jobs. It turns out that the kind of success rate for grant application for young scientists at this time is roughly half of what it was in the early 80s. So in some sense, the senior scientists around in academia and elsewhere were living a much better time and are still in a much better position, I think, in terms of the next generations. So why this kind of lack of success? Well, the argument that Flexner makes is so powerful. And I think it's good to have a conversation about this. There are many forces that are, I think, at fault. Definitely, I think, the shorter attention span of politicians, of companies driving this. But also there's a thing that I would like to call the knowledge paradox, because how does science interact with society? And this is kind of a paradox that whatever we do in research, we kind of dig deeper. And the results of research are more difficult to understand. Now, if you really want to understand what's happening, in an electronic appliance or in a new drug, you have to know a lot of details. So in some sense, it moves infinitely far away. On the other hand, the products of science are everywhere around us. In our pockets, in our phones, in our medicines, everywhere. So I feel this kind of interface between science and society becomes this kind of fractal thing. It's kind of science being atomized. There are these kind of little pockets of knowledge, very specialized, and they're everywhere around us, but they become basically invisible. And it's much more difficult to make the case, I think, these days. And this is something that, Flexner was very much aware of it. And I think the most important point that he makes in the book, and I want to kind of finish on that note, on that theme, is curiosity. He makes basically another point. He says there's this wonderful ability of human beings to see things that aren't there, to imagine things that aren't easily to imagine for most of us. And it's this ability that is so powerful, and it actually is being used, whether it's used in companies, in academic world or in education. I think that actually, I feel, is in some sense perhaps the most important argument why we have to create these kind of environments. As Flexner writes, curiosity, which may or may not eventually eventuate in something useful, although it's good to, somebody said, we have to distinguish applied research and not yet applied research, because how can you argue that something is totally useless and will be forever useless? You never know. For instance, 100 years ago, number theorists were very proud that their field was totally useless and the beauty of the prime numbers. And now, because of coding, actually number theory is at the very center of cybersecurity, etc. I have one colleague who says he wants to prove some big math theorem, factorization of prime numbers, so that he can liberate his subject from the chains of applicability and make it again useless. So you never know, but curiosity, as Flexner writes, it goes back, it's an outstanding characteristic of modern thinking, goes back to Galileo, Bacon, Newton, and it must be absolutely unhampered. And I have a little anecdote. This is Jacobus van het Hof. He was a chemist. In fact, he was the first one to win the Nobel Prize in chemistry. He was Dutch, so at that point, the Dutch totally cornered the market of Nobel Prizes in chemistry. And in fact, his big insight was that molecules were three-dimensional. That is to say, if you take a molecule, you look at its mirror image, it might be a different molecule, and it might have different chemical reactions. That was kind of a new concept. In fact, here you see some of the models in which he was kind of demonstrating this. And he was pretty famous. I actually went to a high school which has a big statue to him, so I passed that statue every day. I think we are not honoring our scientific heroes in that fashion anymore. And I said, this kind of chiral molecules was a very important thing. It's, as you know, all of life sciences depends on the chirality of these molecules from DNA down. But the point was that, he was criticized as a scientist, but as a young scientist by his seniors, that he didn't use too much imagination. I think at that point he was working at the veterinary school, and one colleague said, well, you just consider it more comfortable to mount Pegasus, the flying horse, and just go and fly to the Mount Parnassus and just declare how things are, instead of painstakingly deriving the results. And van 't Hoff was so upset by the criticism that when he was finally made a professor, his inaugural lecture was about imagination in science. And he approached the subject scientifically. So he took a sample of the 200 most famous scientists of the last 200 years and put them in 3 categories. The first category was scientists without imagination, so no interest in the arts, in poetry, in painting, music. The second was those with imagination. And there was a third category, what he called scientists with perverse imagination. That is, they wanted to go into alchemy, they wanted to do metaphysical stuff, etc. And in fact, in that category, it contains Descartes, Leibniz, Newton, Ampere, Wallace. So actually, it's the real famous scientists are in that bucket. And Newton famously became an alchemist, and you can perhaps understand why. Because he, as somebody said, Newton must have been the happiest person who ever lived in the history of the planet, because only one person can be the first to discover that there's a system in the world. Of course, he in some sense invented modern deterministic science. And the fact that if you have unified the laws of gravity for the heavenly bodies and on Earth, and found the fundamental laws of mechanics, why not also find the fundamental laws of history, of religion, of alchemy? You can make gold out of lead. It only takes a nuclear reaction. So it was done 10 years ago. So it's clearly, his imagination reached further than the science of his time would allow. And Einstein also famously said that imagination is more important than knowledge, for knowledge is limited to all we know and understand, while imagination embraces the entire world. Put a picture of a magnet of a young Einstein here, because you all know the story that Einstein, I think was 5-year-old, was given a magnet, and he was fascinated, a compass, fascinated that the needle was always pointing in the right direction. But then he also describes that he walked with the compass through the room, and he noticed, wait a moment, there must be something that is steering the compass. So as a 5-year-old, he was basically discovering the magnetic field. And of course, in some sense, his great contribution to science was to discover the gravitational field and think of it as something permeating all space. So he clearly had a very, very bright imagination at a young age. And I think we're not doing enough to stimulate imagination and creativity. There's this famous test, you have undoubtedly read about it, which is a test that's done with NASA engineers, and 2% of them passed the test, and then there was one person who said, well, let's take the test to 5-year-olds and see how they do. And then 98% pass. At 10-year-old, only 30%, at 15 years, 12%. So I think actually, one instruction we should give to people in the education field, don't touch that button. The imagination probably is turned on at the very beginning, and we put a lot of effort in unlearning skills to imagine and create. And often then at universities and other research institutes, we work very hard to relearn these kind of qualities. And this might be something I feel that the only point where my points differ with Flexner. Flexner felt that basic research scholarship is good as it is. Society should reward it and just let them do whatever they do. In some sense, he was an elitist. When Einstein came to the Institute in 1933, he was invited by President Roosevelt to the White House. Flexner intercepted that letter, and he wrote back, well, you will understand Professor Einstein is a very important scientist, he's very busy, and he has to focus on his research. Einstein was very upset when this happened and made himself be re-invited. He also then opened his own mail, and this might actually be the reason why we have this slightly negative quote about Flexner. So they didn't go along very well. And I think Einstein actually was, in some sense, a perfect example of somebody who was able to reach a large audience and spoke. I mean, he became the canonical scientist, not only because of his scientific work, but also I think his moral compass and how he. One thing I learned, to my surprise, by being in Princeton, is that he spent a lot of time on his wonderful quotations. You might think, oh, he just came up with that. No, he thought about it and he sculpted them just as he sculpted his mathematical equations. And when they were done, he would cut them out and put them in a wooden box. So I would like to say he was actually using Twitter 50 years before it was discovered. And I think this is something that we can know. I think there's a large audience that we can reach out to. And want to close with one final anecdote, which is that now a few years ago I was on Dutch television, and I just had launched a website with experiments for young children. And it's actually a pretty popular website. And they asked me, can you do an experiment? So I should have brought it here, but it's an experiment. You can do it at home. So you take a balloon, fill it with water, and then hold it above somebody's head, and then take a lighter or a match and try to burn a hole in it. It will not work. And I did it, and then I explained why. So, well, you know, if you have an empty kettle on the stove, it gets hot very fast. If it's filled with water, it takes a lot of time. It has to do with thermodynamical properties of water, heat capacity. That's why if you live close to the sea, you have a moderate climate. So I had my little spiel and explained some basic physics. So I felt very happy with that. And the next morning I get an email from a very, very distinguished Dutch physicist. They said, well, Robert, I saw you on television, I liked the experiment, but your explanation was, of course, totally wrong. So I get this sinking feeling, you never speak out. And then he said, no, you didn't show the experiment to explain thermodynamics. You did show the experiment to explain the phenomena of a law of nature. There's a scientific principle that forbids you to burn the hole. And that's why you know that this party trick works. And that actually is something that you should have said. And I think he's right. Now, if you ask me, if there's one thing, if I could wave a magic wand and make everybody in the world understand one thing from science, what would you pick? I probably wouldn't be able to do it in one tweet, but I would like to have everybody understand the scientific method. The fact that you can do experiments, you can learn about facts, you can have some idea, you can disprove it, you learn again, you do another experiment, and that's has been an incredibly successful method. And I think that's something that we can spread, and that's something that people should know. So I feel this perhaps the way to kind of bridge this gap that I worry about, that we have this terrific research. And I said, I don't think there ever have been more opportunities than now. I think every scientist at every time in the history of science has said this, and they were all right, because it's just it's an exponential growing function. So it gets better and better and better. We're in this terrific moment, but we aren't able to make the case. And in some sense, society is kind of starting to decouple. And I think we have to cross that bridge and again make the case that Flexner makes in an extremely powerful way. And so perhaps I want to kind of end by just, because we are in a kind of complicated political situation here and across the world, but I remind you that Flexner wrote about all of this in October 39, which was, as I said, not the best of times. So this is the way he opens the essay. Is it not a curious fact that in a world steeped in irrational hatred which threatened civilization itself, men and women, old and young, detach themselves wholly or partly from the angry current of daily life to devote themselves to the cultivation of beauty, to the extension of knowledge, to the cure of disease, to the amelioration of suffering, just as though fanatics were not simultaneously engaged in spreading pain, in ugliness and suffering. The world has always been a sorry and confused sort of place. Yet poets and artists and scientists have ignored the factors that would, if attended to, paralyze them. So I think these are very wise words. They should be read again. So I'm very happy that I'm now on this kind of book tour with my famous co-author, Abraham Flexner. Thank you very much.
Thank you very much. Wonderful talk. And questions?
Thank you for the fascinating talk. As you say, you're preaching to the choir here.
Yes.
We all came through one or another higher institute of education. We've been propagandized about this quite successfully. We all believe it, and I'm not saying I don't. But one question that's unclear, it's clear that curiosity is a driver for many things. But in modern society, research, including basic research, has become an industry. And Flexner, in some sense, invented that industry with one small institute. So when we now have, I don't know what it is, millions of people engaged in basic and not so basic research, how do we as a society decide how to spend, how much money to spend on that research? Why do we believe that distinguished professors of physics should have upper middle class lifestyles and not just be driven by their curiosity and maybe funding for their equipment? How do we think about these things? And I say this as a member of the class that benefits from all this, of course.
No, it's a very good question. And it's, I mean, in some sense, in its basic form would be indeed, how much time and money and energy should we spend on these efforts? And one thing I find kind of surprising is that even as a society, we made lots of progress. As you said, in some sense, we have seen this whole architecture of the scientific enterprise being built. We didn't spend that much time arguing about why this particular architecture. Now, what are the economic arguments? How are we? I'm advocating in the book of what you need is a kind of a well-balanced portfolio of research projects. How do we look at this? I think actually, honestly, we look in a more deliberate and sensible way at financial investments and how they are, how much risk do you want to take, how much correlation do you want between the various issues, how much long-term, how much short-term, than we do in research. Because in some sense, it's a little bit fly by your pants and intuitive. One thing we see is that these days there are a lot of quantifiable metrics, but they have serious problems, because what we see is that what they do, they drive research around the world all to the same spots. So we get this kind of regression to the mean, and a lot of boring research is being done. So I don't have the answer, but I think we should have a serious conversation about these issues. Also about what is the percentage, so to say, what is the right percentage to spend? I know in this company you can, if you want, spend 20% on other projects. At least it's a number. So I think societies haven't put a number there. I think the first approximation good is to take the world average or something, and that's often how we argue. Are we behind or ahead of our competitors? But I think we need a serious discussion about this. And I think in certain enterprises, I think particularly in the life sciences, the current architecture is totally unsustainable. Now, if you have, it's been indicated, if every researcher kind of breeds 10 more that then have their own research group, you get an exponential function that clearly, these days, if you're a life scientist, you're in your mid-40s when you get your first, typically your first NIH grant. So you basically reach independence at age 45. That's not a very attractive. And so I think that we need more research about that. We have sharper thinking. What is the role of corporations or philanthropy? Who can do what? And why, as a society, do we value this? And as I said, I'm kind of disappointed that the economists have had such great difficulty putting kind of numbers there. As, by the way, they have in the more broader field of education. It's very difficult to make the case there. How does an investment in your education and the kind of education lead to, for instance, your personal gains? But I think here it's really as a society that we have to have. And it's a running target, so to say, because science itself is developing. It's growing, becoming more international. Some of the costs of the experiments are really becoming very large. And I feel that we spent very little time discussing this. We also spend very little time arguing for science. Somebody once told me that the commercial product with the smallest advertising budget is kitchen salt. Now, I've never seen a commercial about kitchen salt, I think. But that science spends less in advertising. And again, if you think that we spend 30 billion from federal money each year on basic research, how much of that is used to kind of spread the word? I think we just assume that by diffusion some of it will flow, and I think so the best thing I can hope is that at least we have a serious discussion to give answers, ideally quantifiable answers, to the very good question that you raised.
So I'll just, something a little different. So I noticed as part of your biography that you're also a trained artist. Can you speak about that?
Well, I'm a failed artist, so I had got my undergraduate in physics, and then as my PhD advisor, 𝐔𝐬𝐻𝐸, the Nobel Prize winner, said, Robert went to physics, get bored, went to art school, got even more bored, and went back. But actually, there's a little anecdote which I think for me was useful, because I usually make the case that actually I spent 2 years in art school, that I learned how to do research in art school. Because when I was a teenager, I was the kind of the character, and perhaps many of you are similar, got to discovered the whole field of science, and would take books and read and do the calculations myself and make drawings and everything, and then went to college, and then of course you do the standard courses, and I had very good grades, but I was basically just focused on getting good grades and passing the test, and I kind of lost interest in the field and started painting. Then I went to art school. I was very serious about that. I think that's my career. But when in art school I certainly felt liberated. I still remember the moment I walked into the bookstore and felt, now I can buy a physics book again. So I bought physics books, started reading it. So it was like, okay, this is for fun. And then I felt, wait a moment, there's something there. But the nice thing in art school is that, success was not passing a test. Success was at the end of the week if you had a big stack of sketches and materials, if you have just explored. And so I made kind of a deal with myself. I go back into physics, because it was my first law. But I will try to conserve or preserve that approach of the artist. That is to say, at the end of the week, I wanted a big stack, not of sketches, but of calculations. And just for fun, you might, tell my students always, if you learn something, try to derive it yourself. Find a way to kind of internalize the result. Do some crazy calculation. The thing I liked best in art school was that you were forced to do things that you didn't like. I liked to paint, and I certainly have to do photography or printing. Actually, it was fun. It was liberating. So, in some sense, for me, spending these 2 years in art was a shortcut to a research career. And so I think that might be a lesson again, that we are not always putting the right emphasis also in the way in which we educate generations. I think particularly in the sciences, because now in fields like math and physics and computer science, it's so easy to devise a perfect test because it's so clear what the right and the wrong answers are. So we focus a lot about the right and wrong answers. I think we should focus more on the right and the wrong questions.
So, given the current political climate,
yes.
Where do you think the center of learning is right now?
Well, it's clearly, there are lots of forces on it. And I think it's not obvious that this country will be the center. So let's first think about, if you think of like research, at this point it's roughly equally distributed, I think, between North America, Europe, and Asia. But a lot of things are happening. But I would say the top segment is still skewed. It's still a large percentage is here in this country. And I think what the United States has, it has these kind of two wonderful characteristics. That first of all, a long, long history of being open to other cultures, other nationalities, and other ideas. It's one of the few countries that's based on a very abstract principle. And the second ingredient is freedom. So autonomy of individuals, but also of institutions. So both have been actually blossoming. And in some sense it's remarkable. Flexner was very critical about American universities, and he predicted they had a very dire future. And he was like totally wrong, because these American universities would blossom in the 40s, 50s, 60s. And they're everywhere. So he was wrong about that. He was also wrong about that large institutions couldn't be excellent, because we had places like Berkeley, which were public institutions, huge and top rank. So the local environment, I would say, in this country is really very well positioned, also with a kind of a pragmatic, empirical attitude, particularly for the sciences. I think these days it definitely is at risk, because these two fundamental points, open to other ideas and other cultures, and this kind of generous financial environment that kind of makes institutions, as we have here in the Boston area, remarkable world-leading institutions, possible. And the competition is eyeing these possibilities, and we all know that Asia is rapidly growing, and it's one of the most fundamental lessons of history to see that commercial centers and centers of learning, they move. They typically move on a scale of a century. I know that if you like the commercial center, like at some point it was in Venice, and then it moved north to like Antwerp, Amsterdam, London, and then it crossed the Atlantic. So you can see these movements on this kind of a scale of decades and century. And I think this country was both the beneficiary of geopolitics and of course of this kind of terrific financial support. And both of this, I think, are at risk. So I feel this is a very dangerous time, because you're really, there are many interventions can do, but this is really kind of something like open heart surgery. This is really the crucial element that's kind of, I think, kind of pumps both the commercial and intellectual heart of this country. And I think it's at risk, and I wouldn't be surprised. So in that sense, even for Flexner, it wasn't obvious, as he didn't write that it moved. He said it might move if you have strength and will to do so. So I think it's at risk, and I think that's something that we should make that case very powerfully. Yeah.
All right. Thank you very much again.
Thank you.